Okay, welcome to probability and genetics. So these laws of inheritance that we've learned about and more that we'll learn about in the future can be used to predict the outcomes of genetic crosses. Now, of course, it's not possible to definitively predict what will happen in the future. So what we're doing is setting up a probability of some occurrences. Now in this, I'm going to walk through some different situations where you can use probability and genetics and define some of the rules that are used. So let's first start by defining probability. So that's the probability of an event is the chance that that event's going to occur in the future. The probability is equal to the number of times the event occurs, divided by the total number of events. Classic way to think about this is with a coin flip. So there's two possible events that you could have if you flip a two-sided coin. It's not weighted. It's either going to be a heads or it's going to be a tails. So if you wanted to know the probability of a heads, then you just divide 1 by the total number of events, which in this case is 2. Probability of a heads is going to be 50%. Probability of a tails is also 50%. Now, independent events are those in which the occurrence of one does not affect the probability of another one. So with the heads and the tails, the probability of flipping a head on one is not going to affect the probability of flipping a tail. Every time you flip it, you're going to get either a heads or a tails. So this also applies in terms of our rules about gamete formation and what we talked about in terms of the law of independent assortment. So that's how one of the links between probability and genetics. And to illustrate that, let's think about a cross between two heterozygotes. So it's a simple monohybrid cross. In this, when we do a Punnett square, a lot of times what students don't realize is that these up here and these down here represent the haploid gametes from these two individuals. So for example, these are the gametes from this individual. These are the possible gametes from that individual. So the probability of this individual producing a big A allele is simply in the gametes is simply 1/2. The probability of producing a little a is also 1/2 for that individual. So half of the gametes are going to be big A and half are going to be little a. Then we're putting them together and we're producing probabilities for these different genotypes in here. Now, one of the first rules that we'll encounter in genetics or even with coin tosses is that when two or more events, when you're interested in the probability of two or more events, they're going to be equal to the product of their respective probabilities. Another way to think of this is when you want this and that to happen, you have to multiply them. So and equals multiply. Now, an illustration of this is in this question. So remember I said early on that words really matter. How questions are asked matter. In this question, where it says, what is the probability of flipping a head and then a tail with two coin flips? That means that on the first flip, you want a head, and then on the second flip, you want a tail. That's the only order that's actually going to satisfy this condition here, a head and then a tail. So we know what the probability of a head is. That's simply 1/2 for a coin. The probability for a tail is simply 1/2. Now the probability that you get a head then a tail, or a head and a tail, is going to be equal to 1/2 times 1/2, which equals 1/4. Now there's a couple of other rules that we're going to talk about too. There's the sum rule, and there's also a binomial expansion. Now, first, let's illustrate this in the case, and let's apply it specifically in the case of genetics. Here we have a disease that's referred to as congenital analgesia, and this is actually a real disease. Affected individuals can have trouble distinguishing between sensations. So extreme sensations may not be perceived as very painful. This is considered a recessive trait in humans. So for you to be affected or affected individuals are actually going to have a recessive, or going to be a homozygous recessive. So they'd be little p in this situation. Now, the question says that if you have two heterozygous individuals that are planning to start a family, what's the probability that the couple's first 3 children will have congenital analgesia? Now, like that last problem, this is an example of an ordered event. We want it to happen in a specific way. So let's look at how we actually solve the problem. I've repeated the question here and provided the alleles. I recommend that y'all write those kind of things out when you're solving these problems. So what do we know from this question? We know that congenital analgesia in the previous lineup about this disease is that this is a recessive trait. So that means that what we're really interested in this question is individuals that are little p, because they're going to be affected by this condition. Also in this question, notice it says first 3 children. So that's child number 1, 2, and 3. They need to have this genotype. And these are little p's. Now, what is the probability of getting a homozygous recessive from a cross of 2 heterozygotes? That's your simple Punnett square. I know that you can work this out yourself, but I know that the probability of a little p is equal to 1/4. And we're using the specific genotypes. Does that work for the phenotypic ratio too? It should. So the probability of this event here, this first event occurring, is 1/4. The probability of the second event of a little p is also 1/4, because these are independent events. Then the probability of that third event of being a homozygous recessive is also 1/4. So we want the first 3 children. That means I want this and this and this to occur. So that means that we have to multiply 1/4 times 1/4 times 1/4, which is 1/64. So the probability of having 3 children that are the first 3 children affected by congenital analgesia is actually 1/64. You can convert this into a percentage and say that approximately 1.6% of the time this will occur. So this is a relatively rare kind of occurrence. So that's the application of the product rule. Let's talk about the sum rule. And in this, what we're trying to do is to calculate probability for unordered events. So this is when we're dealing with 2 or more mutually exclusive events, and their occurrence is equal to the sum of their respective probabilities. Now I know that sounds kind of confusing, so let's talk about it a little bit more. So we can do a very simple very simple kind of probability question using dice, or you could use it about genotypes also. But here we're just going to do the probability of rolling a 3 or. Every time you see an or, you should think sum or addition. 3 or 4 with 1 dice. So to figure this question out, we need to know the probability of rolling a 3, and we need to know the probability of rolling a 4. So the individual probability of rolling a 3 with 1 dice, we're going to ignore this dice over here, probability of rolling a 3 without 1 dice is simply equal to 1/6. This is a 6-sided dice. There's 6 possibilities, 1, 2, 3, 4, 5, 6. So 1 out of those is actually going to be a 3. The probability of rolling a 4 with 1 die is actually 1 out of 6 also. They turn out to be the same. Now if I want this condition or this event or the second event to happen, I have to do what? I have to add them, because this is an or situation. And that gives me 2, 6 or 1/3. So 1/3 is the probability of rolling a 3 or a 4 with one dice. Now you can put these rules together. The easiest way to do this when you've got outcomes of more than 3 is to use a binomial expansion, and that's detailed in your book. I'm going to restrict or focus on 3 outcomes in all the problems that I give to you. This is a good thing to know, especially when you're dealing with 4 or 5 or 6 kind of outcomes, and it's relatively easy to work through. But we'll just deal with 3 here and explain the idea behind why you would have to use both of these product and sum rules together. So here's a situation where I'm asking, what is the probability of having 2 reds and a green? And I've given you the probability of a red as 1/2 and the probability of green as 1/2. So we know those individual probabilities. What we don't know is the order. Okay, so this is an unordered event. Okay, so to illustrate that, let's think about it. We've just got to satisfy the condition of 2 reds and a green. So we could have a red, and a green. We could have a red first, and then a green, and then a red. Or we could have a green first, and then a red, and a red. These are 3 mutually exclusive scenarios. 1, 2, and 3. Each of these has their own probability attached to them. And for our example, the probability of this series occurring is simply going to be 1/2 times 1/2 times 1/2. Right? Because I want a red and a green. So the overall probability of that is simply 1 over 2 times 2 is 1/8. Now, is the probability of this second scenario happening any different from the probability of this scenario happening? No, we still have the same probabilities here. We're going to treat them the same way because these are this one and this one are mutually exclusive events. Within those events, I'm saying I want this still and this and this. So our probability for all of these 3 events is simply 1/8 because we're not changing the individual probabilities of these independent events occurring. We're just, now what we have to account for is the different ways, either different scenarios, if you will, 1, 2, or 3, that we can satisfy this condition of 2 greens and a red. So after we've calculated the individual probabilities for this, now we apply the product rule. No, we apply the sum rule. So that means that we're adding 1/8 plus 1/8 plus 1/8 to get 3/8. That is the overall probability of having 2 reds and a green. We're not saying what order, so that's an unordered event. And we'll see a classic way to think about this, or a classic way to do this is for situations of birth order. That's another good way to do it. So we apply the product rule to calculate the individual probability of these independent events. Then we apply the sum rule to calculate the overall probability of satisfying this condition. And I hope that helps with probability.